Okay, we're going to be starting some studies on particle physics looking at the Standard Model. But before we do that, it's important to just take a moment to discuss orders of magnitude and scientific notation. So, if you think about in the past, as when people have been exploring the universe around them, they've been observing and making measurements of different things. So in the past, before we have the technologies that we have available to us, scientific discovery was on a scale that reflected what we can observe and measure. So if you look back at in history, back as like way back to the time of, say, the Pharaoh, the ancient Egyptians, ancient civilizations, the Greeks, Babylonians, these people were doing they were doing good science, they were doing real science, they were making breakthroughs in mathematics, but they didn't have telescopes, they didn't have microscopes, so what they observed was just what they could see. And they made measurements, so the early measurements that people would make, they would use their body, they would use the length of their hand, the length of their fingers to their elbow, they would use a stride to measure distances. So it was all relative to what was physically possible for them to do and to measure. They had no way of probing the very small or the very large. They had no idea that there was a whole universe stretching out beyond what they could observe in the night sky, and they had no way of knowing that there was whole ecosystems of microbes and viruses or even just microscopic single-celled organisms, that they had no idea that these things existed because there was no way they could probe them. So as we progressed, that's not how we so progressed. As we progressed and developed technologies to probe the very large and very small, we developed new scales to measure. So if we think, oops, so let's think about this. We'll think about the three things we would measure. We measure distances, we measure time, and we measure mass. So typically in the past we would measure distances kind of 10 to the minus 3 to 10 to the 2 meters. So when we say 10 to the 3, 10 to the minus 3, that is 0.123. 10 to the 2 is 1 with 2 zeros. So you've got the 2 here refers to 2 zeros. The minus 3 is how many points after the decimal place. But we'll go into a bit more of that in the scientific notation. So this is the distances that we can measure comfortably without any additional technology. 10 to the minus 3 is quite small, but we can do it. It's just fraction of a millimetre, and obviously 100 metres we can measure that. Time, 10 to the 0, so 1 to 10 to the 2 seconds, so it's 1 second to about 100 seconds. We can measure those time scales without any technology to aid us. And then for masses, 10 to the 1 to about 10 to the 2 kilograms. So the kind of the range in which human masses kind of dwell in is what we can measure. Obviously, the ancients would have been familiar with masses less than that, but this is what's easiest to measure with like rudimentary balances and such like. So once we were able to develop ways of measuring very small and very large, we needed a new way of writing very small and very large numbers. So let's consider the speed of light. This is probably not new to you, but we'll just review it anyway. So this is the speed of light in standard scientific notation. And in these numbers we call this part, the number part here, the mantissa, and it's quoted with 1 or non-zero digits. There's always either there might be a digit there or a 0 before the there's a non-zero digit before the decimal place, and the degree of accuracy is determined by how many significant figures that we have in the mantissa. This part here, the 10 to the 8, is the exponent, and it's always quoted as an integer power. Now if you think what this means the exponent here, 10 to the 8, is 1 followed by 8 zeros. This number is also called the order of magnitude of the quantity. Now if we were to write this out in just normal form, we'd have 2 and then 1, 2, 3, 4, 5, 6, 7, 8. Meters per second, and that's cumbersome, it's messy, it's easy to write one too many or one too few zeros, hence we write it in scientific notation. In the opposite direction we have the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. And this time here we've got our mantissa. This time is to 3 significant figures, and the exponent here means 1 followed by 31 zeros. The inverse of 1, sorry. And if we were to write all that out, it'd be 0.000000000 down to 911 kilograms with all our 31 zeros, which is very small, very long, and very cumbersome to write, and so we will write it like this. If we were to consider, let's consider the large universal scale. So on a universal scale, so we're talking about galaxies in the universe, the observable distance that is known that we can observe is 10 to the 26 meters. And later on we'll discover that when we're dealing with astronomical distances, there's astronomical units that we use, so we're not having to deal with these kind of orders of magnitude in meters. The times that we talk about are 10 to the 10 years, or 10 to the 17 seconds. So that's in reference to the Big Bang. And the order of magnitude of masses that we're talking about is 10 to the 32 kilograms, which is the mass of the most massive star that we know, and 10 to the 50 kilograms to 10 to the 60 kilograms is the mass range that is believed to be the mass of the entire universe. So these are huge numbers, and we throw these kind of numbers out there, we discuss them with these massive numbers, and it's so hard for us to really comprehend the scale that these are dealing in. We say that the mass of the known universe is between 10 to the 50 and 10 to the 60. That's a huge fluctuation, and yet we just can't comprehend it because we live in our own perception of measurement. And the same is true when we go to the subatomic level. So the distances that are involved at the subatomic level, if we've got 10 to the minus 10 meters, that's the diameter of a typical atom. 10 to the minus 14 meters is the diameter of a typical nucleus. Look at the difference in the order of scale. The difference is huge. From that we can see that most of the atom is empty space. 10 to the minus 15 meters is the diameter of a proton or a neutron, and 10 to the minus 18 meters is the diameter of an electron. At a subatomic level, the scales of time, we're talking at things happening really, really quickly. 10 to the minus 22 seconds is the time of a proton will take to cross the nucleus. These things move exceedingly quickly. And the masses we're talking about, 10 to the minus 27 kilograms is the proton neutron mass. They're not actually identical masses, but they're of the same order of magnitude, and they're very, very similar. And 10 to the minus 31 kilograms is the electron mass. So what we can see from this is, compared to the proton and neutron, the electron is absolutely tiny. And to an electron, a proton and a neutron are really quite massive when you look at the orders of magnitude that we're dealing with here. Now, as we develop the technologies to probe into the subatomic, this happened in the early 20th century, so the beginning of the 20th century, scientists began to probe the subatomic. And this opened up a whole new area and field of physics that they weren't really thought existed up until this point, they were able to measure smaller and smaller dimensions and even be able to probe the physical properties of subatomic particles. It became clear that the particles in the nucleus, which we call nucleons, were composed of smaller particles. So each nucleon was made up of a collection of smaller particles, which were more fundamental. So, but up until that point, people thought that they knew the nucleus was protons and neutrons. That was discovered, and then they discovered that these protons and neutrons, they thought these were fundamental particles. They couldn't be divided any further. They then discovered that within the protons and neutrons were even smaller particles called quarks. And from this, physicists developed what is now known as the Standard Model of Fundamental Particles, and that described the property. From this, they were able to describe the properties of these fundamental particles. They were able to anticipate and predict the existence of other subatomic particles that hadn't been found through experiment, and they were able to take this model and then apply it to experimentation to probe the subatomic level, to go and look for these particles that they predicted existed because of the maths that was involved in the particle physics, and right up until 2013, they were still discovering and looking for the different parts of the Standard Model. And with the discovery of the Higgs boson in 2013, that was for example, so to speak, the crowning jewel of particle physics, where it all kind of came back to these measurements and these experiments that began in the 20th century that opened up the subatomic. So what we're going to do now is we're going to go on from there and describe and talk about the history of the Standard Model, what it actually is, what it looks like. It's one of these things in physics and science that is both beautifully simple but also beautifully complex. So that'll be our next lesson.